SwayamPrabha. Digital India. Educated India.
Okay, so let's begin. Yeah, so we were discussing this monotone lower bound for the click function last time. So basically, just to recap the problem. So the click function is basically a function which takes a graph as an input and outputs 1. It takes a graph G, and so click, it is defined for a parameter k. So click kn takes a graph G as an input and outputs 1 if the graph has a click of size k. So click is a complete graph. Okay, and we want to show that there is no monotone circuit, that is, there is no circuit consisting of only AND and OR gates which accepts the click function, and or we will show that any monotone circuit which accepts the click function must have exponential size. So there is no polynomial sized monotone circuit for click. So what we argued, so what we showed last time is the following result, that or the following notations and results. So this is the click indicator. So for a set S in a graph G, it outputs 1, the function outputs 1 if S is a click in G and 0 otherwise. An approximator is basically, so we are trying to approximate a gate, so it can either be 0 or 1, or it is disjunction, it is an OR of at most m click indicators. Okay, so we will show that, and basically our goal is to show that any gate can be approximated by a approximator, okay, whether it is an AND gate or OR gate, that is what we showed. Now a sunflower is a collection of sets with a common intersection. Okay, so you have a collection of sets, any two sets have some intersection, and if all, for all pairs of sets, if that intersection is the same, then we call it a sunflower. We showed the sunflower lemma that if we have a collection of sets where each set has size bounded by some L and the collection has at least so many sets, then that collection has a sunflower, okay, with p petals. Now the plucking operation is basically, if you have a sunflower, if you show that some set has a sunflower, then you take a sunflower and you replace it with the center of the sunflower. So the center is basically the common intersection. So we we saw all of this last time. Now approximating these two gates. So suppose if I have two functions, okay, f and g, okay, where f, let us say, is already approximated by an OR of click indicators, and g is already approximated by some, it's by an OR of click indicators. So sorry, this is not in, this is equal to. So f and g are already approximated, and again when I say approximated, it has to be approximated by at most m click indicators. Okay, then if I want to, if I consider f or g, this is the approximation for f or g. What we do, we basically look at, so basically f or g will be now an OR of all click indicators over a and b, which can go as large as 2m. So then we showed that if it goes as large as 2m, I will repeatedly apply the plucking procedure until and unless that size comes below m prime. Okay, and this is the definition for it. Now for AND, it is a little bit more tricky. So suppose if I have an AND of two functions f and g, now think of it, so f and g, if I have an AND of two functions f and g, the gate outputs 1 if both f and g output 1. F and g will, and f and g are disjunction of two, yeah, so these click indicators. So if both f and g have to be 1, there has to be some xi here which is 1 and some yi here which is 1, some yj here which is 1. So now what we do is that we look at all, of course, xi, yj, and now first what we do is we replace, so this is not a click indicator, right. So first we replace this with c x union y, okay. Of course this is changing the function. So then what we do is that it is first of all increasing the size beyond m, because x union y can go as large as 2m now, no 2l, right, 2l. So we remove all, so I think this I did not mention last time, right. So in the definition last time I forgot to mention this second step, so you can write it over there. So the second step is we remove all those x union y's such that x union y is greater than n. We just drop those click indicators, okay. So you can note it down, I think I forgot to mention this step. Now still I can have a total of at most m square many such indicators, because A has size at most m, B has size at most m. So xi union yj can be at most m square many such pairs. So now I do the same thing as OR. So I it is bigger than m, so we will take m to be this quantity. So it is m square which is bigger than m. So there is a sunflower. So I pick that sunflower, I replace it with its center, and I keep on doing this, and we showed that, well, it is very easy to see that after at most m square many pluckings, this size would come down below m. Okay, so this is what we saw, and then we saw these two distributions. So this is like a smallest graph, a minimal graph which has a clique of size k. So given from n, given a discrete graph on n vertices, that is no edges present, I just randomly pick some k vertices and make that into a clique. A no distribution is basically again I take a discrete graph on n vertices. Now I randomly pick a coloring function, okay. Think of C as a coloring function which assigns a color between 1 to k minus 1 to all the vertices, and now I will add an edge. So I can, okay, let me just and add edge u comma v, let us say in G, if and only if they are colored differently, okay. And it is very easy to see that this graph will not have a clique, because you will never find a set of k vertices which are colored differently, because you only have k minus 1 colors, okay. So this is what we have seen so far, right. So now how do we proceed? So like as I said, the idea of the proof is we will show the following. So we will show that if a circuit, if a monotone circuit computes, we'll show that if a approximator computes clique, then it must have some large size, okay, it must have size bigger than some quantity. And on the other direction, we will show that each gate can be computed by a, each gate can be approximated well, okay. So there is only a small number of inputs on which that approximation will fail, and then we will show how to combine these two to get the lower bound, okay. So let me begin. Okay, I will write it here, right. Okay. So, okay, fine. So each approximator is either 0 or outputs 1 on at least one minus L choose 2 by k minus 1 times k minus 1 to the power of n negative test graphs. So this is kind of showing the first part that I said, right, that each approximator doesn't do too well. So basically if it is a negative test graph, then the approximator should output what, 0, right. But what we are showing is that well, if it is outputting, I mean it either outputs 0, which is okay, or it is outputting 1 on this many negative test graph. Okay, so it is output. So the approximator is either 0, or if it is a negative test graph, then it is outputting 1 on a very large number of them, which should not be the case. So how do we prove that? So let C equal to be an approximator huh? I am not talking about positive here. So I am just saying that each approximate, actually when I say 0, it is not just 0, each approximator is either identically 0, that is irrespective of the input it is 0. Okay. So basically what this is saying is that either an approximator is identically 0, or if you give it a negative test graph, then on this many negative test graph it is giving a wrong answer. Okay. So if you are giving it a negative test graph, then it should output a 0, but I am saying is that on a very large number of them it is giving 1. Yes, it should output 1, on a negative it should output 0, that is the idea.
So we are not talking about on positive.
No, we are not talking. No, we are not talking about positive here. We don't need positive. That is not identically 0. Okay, so take a approximator that is not 0. So if it is identically 0, then it is case 1. Suppose it is not identically 0, then we have to show this. Okay. So what does it mean to say it is not identically 0? Well, it means that there is some xi over here which is 1. Okay. And what follows without any loss, I mean what we can say is that C is greater than or equal to, no, it is not xi, it is, did I write xi? It is Cxi, it is the click indicator. I hope I wrote it correctly elsewhere. Yeah. Okay, so now C is greater than or equal to Cx1. Why is this? So, exactly. If Cx1 is 1, then of course C is 1. That follows by definition. So let size of x1 be some L prime. Okay. Now we will argue for when will this approximator output 1. Okay. So okay. So for a negative test graph, probability that Cx1 is equal to 0 is what? When is Cx1 equal to 0? So Cx1 is 0 if x1 does not form a click. When will x1 not form a click? If let us say there are two vertices in x1 which are colored the same. When will two vertices be colored the same? So, I mean, what is the probability that two vertices will be colored the same? The probability that two vertices will be colored the same is, well, upper bounded by. So, if I fix two vertices and they are, what is the probability that they are colored the same? It is 1 over k minus 1, because one vertex can be colored anything, but now this other vertex must have this fixed color of the first vertex. And now the ways I can choose two vertices is L prime choose 2, right. So it is L prime choose 2 times 1 over k minus 1. Now L prime is less than L, so this is L choose 2 by k minus 1, right. And yeah, I think we don't need much more here. So probability that Cx1 is equal to 1 is greater than or equal to 1 minus L choose 2 by k minus 1, and probability that, now this is the probability that for a negative test graph it x1 forms a clique. Now the number of negative, and if x1 forms a clique, of course then c is equal to 1 and the graph, I mean the approximator is failing. So the number of negative test graphs for which the approximator fails is at least the total number of negative test graphs. How many negative test graphs are there? K minus 1 to the power n, this also we mentioned last time, times this probability. Okay, that completes the proof. Okay. Yeah, and please stop me if something is not clear, because there are, I mean the proof is not very difficult, but there are small ideas, lots of small ideas, and which portion, which, this one, why is it less than this? So okay, so what do you mean by Cx1 equal to 0? It means that x1 does not form a clique. When does x1 does not form a clique? If there exist two vertices which have the same color. That means there is no edge between them, right? What is the probability that there exist two vertices which have the same color? First of all, there exist two vertices, so there are L prime choose L prime many vertices in x1. So I can choose two vertices in L prime choose 2 many ways, and the probability that for if two fixed vertices they have the same color is 1 over k minus 1, because one vertex can get any color, any of the k minus 1 color, but this other vertex need to have only that color. Okay, so that's fine. Okay. Any approximator that is not identically 0. That if that approximator is, if the input is a negative test graph, then on at least so many negative test graph that approximator is failing. Okay. So this probability is over the choice of the graph. Okay. So this is over n over here. So you are choosing a graph from this distribution n, and the probability that it is failing. Okay. Okay. Now let me move to the next lemma. So f or g less than or equal to f, the approximate OR of g is always true, but F and G less than or equal to F, the approximate AND of G fails for at most m square into n minus L minus 1 divided by k minus L minus 1 positive test graphs. Okay. So what we are saying is that if you look at this inequality, this is always true, but this other inequality will fail for a small number of graphs, okay, for some bounded number of positive test graphs. So how do we show the first one? So let me write them as 1 and 2 maybe. So look at the definition of OR. Okay. So how do we do OR? So basically, if I consider all the sets in A and B, then I get exactly F or G. But how do I get F approximate OR of G? By applying the plucking procedure. What do I do in the plucking procedure? I take a sunflower. Okay, so basically, since this size is bigger than M, there exists a sunflower. So I take a sunflower and I replace all the petals of that sunflower with the center. Okay. So what happens when I do that? What happens when I replace the petals with the center? What happens to the value of these two functions? So when would this fail? This would fail if F approximate OR of G is greater than F OR of G, right? So basically, this is 1, but this is 0, which means that in the approximate OR, I have a click. One of these zi's have a click, but none of these two guys had a click. Correct? Oh yeah. This is strictly greater than this. So this is 1, but this is 0. Correct. Yeah. So this zi's do not have a click, but there was a click somewhere over here, right? Now, is that possible? Why not? Huh? Why? Because the center of the sunflower is a subset of the petals, right? So each of these XYs are petals, and now if I apply the plucking procedure, I am replacing a collection of petals with their center. Now, if the petals had a click, the center must have a click, it's a subset. Okay. So the plucking procedure cannot destroy a click. Okay, you can potentially increase a click, but it cannot destroy a click. Okay. So the plucking operation cannot destroy, or okay, let me write it a little more. So after a plucking operation, a click in a petal implies click in the center. Right. So therefore, clicks are not destroyed, and that is the only thing that we do for. Now let's move to the AND. So now what do we do for the AND? So first of all, we replace Cx and Cy with Cx union y. Okay. Does this? So once again, when will this fail? So this will fail if f approximate AND of G is greater than f AND of G, that is, sorry, is less than f AND of G. So yeah, so this is 0, but this is 1, right. So what happens as a result of the first step? Can this fail in the first step? The key is we are looking at positive test graphs. That is the key. See, this of course can fail in general. If you look at a general graph, if x and y have a click, it does not mean that x union y will have a click. There is no guarantee. But what about a positive test graph? What is a positive test graph? It is a graph which has only one click of size k, right. So if there is a click, if you take a set x from that graph which has a click, and if you take a set y from that graph which has a click, what does this say about x and y? It must belong to this set of k vertices which found the click, and therefore x union y also has a click. Okay, so this is true because it is a positive test graph. Okay, so since it's a positive test graph, therefore if x and y have a click, then x union y, or x and y, if x and y is a click, not have a click, have is not the correct word, if x union y, if x and y are clicks, then x union y is also a click. Okay, that is the first part. Now what is the second part? The second part is we are deleting all sets which have size bigger than L. Now this can of course destroy a click. I mean, maybe there was some click on a set x union y, but that got deleted now. So we will count how many such x union y's get deleted which potentially had a click. Okay. So the second step can potentially destroy a click. So what do we need to count? That, well, in a graph, okay, so suppose I have this graph on n vertices, and I have this set of size, let's say at most L over here, sorry, so x union y is greater than L, okay, so this is n, and I have a this x union y which is bigger than L, and I am throwing this out. How many positive test graphs are getting destroyed as a result of throwing this out? So when will a positive test graph get destroyed as a result of throwing this out? When this formed a click. Okay, so essentially I have to count that the number of positive test graphs where X union Y was a clique. Okay. Now, how do I choose a positive test graph? A positive test graph is chosen by choosing some k vertices. Okay. So, this would have been a clique. So, when would this have been a clique? On what kind of a choice for the positive test graph would this have been a clique? If X union Y is contained in the set that is picked, right. So, if the k vertices that I am picking contains this, right. So, now the probability the count boils down to how many ways can I pick these k vertices such that this set of size bigger than L, actually greater than or equal, so it will bigger than L means greater than or equal to L plus 1. So, I can maybe write here as L plus 1 here, this is here. How many ways can I pick this k vertices such that it contains these L plus 1 vertices, right. And what is that count? What will that be? Precisely. N minus L plus 1, choose k minus L minus 1, right, because it is L plus 1 here, yeah. Right. So, these L plus 1 vertices are anywhere there is no way in which you can tinker with them. Now, the remaining k minus L minus 1 vertices, how many ways are there of choosing them among the remaining vertices in this larger set? Okay. Why should the k vertices be?
In the donut shape, like within the outside of L plus 1 but inside of that. So why are we taking the k vertices?
No, because I want to count when will this set, so this is my X union Y, when was this a clique? So, this was a clique if this choice that I made for the k vertices was a superset of X union Y, okay, when it contained this, because the rest of the graph is empty, it does not have any edges. So, the only way in which X union Y could have been a clique if these k vertices were a superset of X union Y. Okay. So, I will keep this part, I will not erase this for now. Let me erase the proof of lemma 1. And how many times does this happen, or how many such X union Ys could have been removed? So, the total number of such X union Y is bounded by m square. So, I mean trivially let us take it as m square, I mean worst case everything was greater than L, that could happen. So, anyway, so the number of positive tests on which second step fail is at most m square into n minus L minus 1 divided by k minus L minus 1. Right. Now, what about the third step? If I apply the plucking procedure what happens to the approximation? So once again note that the plucking procedure does not destroy a click, right. So if a petal had a click, then the leaves also, I mean the center also has a click. So therefore, as a result of the plucking procedure, this does not get disrupted. So that is actually doesn't matter what graph it is. So the third step is plucking does not destroy a click. Okay. So therefore, the lemma follows. Okay.